Okay, yeah, today we will talk about two attacks on how to manipulate the memory subsystem to break trusted execution environments. No, not in focus. Ah, there we go. A little bit of delay. Yeah, so a little bit of motivation. First, one of the prime scenarios for trusted execution environments right now is in the cloud, and if you rent a regular VM from a cloud provider, then in theory they have the technical means to access all of the data that's inside your VM. And the pitch of trusted execution environments in this context is to entirely lock out the cloud provider to enable the user to compute on a remote machine with similar privacy guarantees than they have on their local machine. At least that's the pitch. And one particularly interesting use case is to use this in the context of confidential AI inference, because there you would ideally want to protect the IP of the model owner so that the model is not stolen from a cloud provider, but you'd also want to protect the query and the generated answer of the user from both the model owner and the cloud provider. That's one very interesting use case right now. However, this is a really strong attacker model. These TEs try to defend against privileged software level attackers, so administrators or root users on the system, and also to some extent against hardware level attackers. And as you can imagine, this is a very large attack surface. This has already led to quite a few attacks, and we will now show two more. But before we dive into the details, we need to understand how these isolation mechanisms of these TEs work. And the first thing that we need here is memory encryption for the DRAM. And that's because otherwise a privileged software level attacker, for example, could simply read out the DRAM and get the plain text, or a hardware level attacker could do a cold boot attack or an interposer attack to get the data. So we really need confidentiality for our DRAM via encryption. But ideally, we also want to have integrity and freshness so that we can mitigate more advanced attacks where an attacker can repeatedly read or manipulate the memory. And the initial Intel SGX design had all of these properties. However, it came with the drawback that it didn't scale to large memory sizes, mainly due to the way that the constructions that we need to provide integrity and freshness in this use case. However, the industry wanted to run larger programs in trusted execution environments, so the subsequent version, which is able to scale to large memory sizes, switched to a different encryption engine and dropped these two properties. And then SEV-SNP, which protects VMs instead of processes, basically did the same thing. Intel TDX is slightly stronger in the sense that they do have a cryptographic integrity protection. However, to some extent also relies on a brute force prevention mechanism because the MAC that they use is too short otherwise. And then finally, ARM-CCA does currently not mention any integrity protection or freshness in their specs for memory encryption, but it's also not out yet, so it might change. So the takeaway here is that currently we don't have any freshness guarantees from the encryption system on these scalable TEs, and only in TDX we have integrity. And this means they need to implement an additional mechanism to prevent these attacks that would otherwise be possible, for example, a memory replay attack. And they do this by implementing an additional access right mechanism that even applies to privileged software level attackers. And the rough idea here is that we define a space in a region of memory in the physical address space where the data of the TE lives, and this mechanism would then prevent even these privileged software components from accessing this part of the memory, so that they are restricted to the non-TE memory. And this is the part where we want to see if we can overcome it with our attack by asking the question whether we can maybe manipulate the DIMM and the memory subsystem in such a way that we can overcome this isolation. And for this, we need to understand a bit more what actually happens when we do a memory access. So we have these two different address spaces. We have the physical address space, which is what the CPU sees, and then the memory translation unit translates this into DRAM addresses, which we actually send to the DRAM. And the implicit assumption here is that if we have two different physical addresses, they should of course map to two different addresses on the DRAM. And why do we have this translation step to begin with? And this is mainly because, as we already seen in many other talks, that DRAM internally is organized slightly different than this flat physical address space, in the sense that we have these ranks, banks, columns, and rows, and the physical address space is some form of abstraction over that. Okay, and the construction of this physical address to DRAM mapping, this relies on something that's called the SPD chip. That's a small EEPROM chip, so that's a storage chip basically that's on each memory module, and that contains metadata about the DIMM, like the size, the speed, the manufacturer, and so on. In fact, it's quite a long table, but one particularly interesting entry in this SPD metadata is this SDRAM addressing field, which encodes the number of row bits and column bits. And so basically, it provides information about the size of the DIMM. And this is what we will manipulate in the following to overcome these mechanisms. So when the system boots, the BIOS communicates with this SPD chip on the DIMM to set up this address translation. So DIMM basically says I'm 16 GB large and I have this many rows, and then the BIOS goes ahead and configures the memory controller to create this nice mapping. And the idea of the attack is now to manipulate the DIMM by adding an additional row bit, so basically advertising a size that's twice the size of the actual DIMM. And the BIOS simply has to trust this information because it has no way to verify it, so it goes ahead and creates an address space that's actually twice as large. So we'll end up with two addresses in the physical address space that map to two DRAM addresses that will only differ in this additional row bit that we added. And now the really surprising thing is when we send this access to DRAM, we don't get a crash, but the DRAM will simply ignore this additional row bit and silently route this access to this one memory location. So we end up with these two physical addresses, which for the CPU clearly point to two different memory locations, but in the end we read the same memory from DRAM. And thus we have this aliasing primitive. And how can we do this manipulation? For this we explored two angles. The first one uses additional hardware. So we have this small interposer and in Raspberry Pi, and you plug in the memory module once, and then you can directly attach wires to this SPD chip. And the SPD chip only has a safety mechanism to prevent accidental override. So it's basically a lock bit that you can unset, and then you can just manipulate the data without any integrity protection. And the cool thing here is that you only need to do this once, and then you can send the DIMM to the data center, so you don't need to be physically present or manipulate something inside the server cage. And total cost is quite low. It's about $10, so it's not a really advanced attack in that sense. And then we also looked at whether it's possible to do this manipulation in software, because the BIOS can communicate with this SPD chip over the SM bus, and if the BIOS doesn't add locking mechanisms, then it's in principle possible to also do this manipulation as long as the SPD doesn't have this lock bit set. And we found that this is actually the case for two UDIMMs. But the small caveat here is that these UDIMMs cannot be used in these server systems where we have SGX and SEV nowadays. So for the TE attack, this is not as relevant. Okay, so now we understand how we can manipulate the SPD and that we have this aliasing mechanism. So how can we use this for our TEs? Let's assume in blue here we have our TE and it writes data to memory, so it gets encrypted with the memory encryption key K0 of the TE. And now we use, as an attacker, our alias to read from that memory location, which we previously couldn't do because of this access prevention mechanism. However, we still don't get the plain text because we have a different memory encryption key. So we get this value here, which is basically some random string because the keys don't match. And now after some time, the TE will write a different value to memory, but now we can take our value and replay it, because you can also write. And now, since we don't have any integrity protection in the memory encryption system, this won't be detected on the next access. Now we have a small demo for that. Terminal window. These are slow, it's not getting picked up. No, on the screen. Oh. You didn't mirror. Oh, this will be slightly inconvenient. Okay, but here on the left hand side we have our SEV-VM that's currently running somewhere in Leuven. And we allocated a memory buffer here and set it to 0. And on the right hand side we have our attacker on the hypervisor side, where we basically already provided the memory address of this buffer here. So this is a slightly simplified scenario. And now we can capture the ciphertext here, switch over to the other side, and there we will now overwrite this buffer with all Fs. And now we can go back to the other side and do the replay. And of course, we don't see anything there. But now if we go back to our victim and we access the memory again, then we see that we have all zeros. So this is a basic replay primitive, which is already quite cool. It's a bit laggy, but we'll get there eventually. Yeah, so this is already quite cool, but we found that with this simple primitive, there's a really nice way to actually break the attestation mechanism of SEV-SNP and thus all trust in the system. And yeah, now I will walk you through that. So we have basically 3 parties here. We have the guest owner, which is the user, and they supply the hypervisor with an image of a VM that they want to start. And then the hypervisor works with the secure processor. This is the hardware root of trust of SEV. And this chip will then do the actual loading, because we need access to these memory encryption keys for that. And the hypervisor obviously is not allowed to have them. But while this allows the hypervisor to now load arbitrary data into this VM, the secure processor will also maintain a hash of all of the data that has been loaded. And then later on during attestation, the user can verify that hash to compare it to the expected value, so that they can check that the hypervisor only loaded the data that they actually wanted to be loaded. And what we can now do is we can capture this hash value with our mechanism, and then we abort and restart this process. But instead of launching the original image, we launch a modified image that contains some kind of backdoor. Again, we start this encryption process, and of course the hash will now be different. However, we can now use our replay primitive and replay this previously captured hash. And that's possible because this guest context page always uses the same memory encryption key. So VMs will always use a new memory encryption key. When you stop them and restart them, you generate a new one, but this guest context that's owned by the secure processor uses the same memory encryption key. And after we've done this replay, it's not really surprising that the attestation mechanism does not pick this up, because the hash value in memory matches the expected value. So we just started the backdoored VM without any means for the user to detect that. And there's also a small demo for that. Yeah, so now we are, maybe it's easier if I do it like this. Now we are in the VM, and we query our attestation report. And this is this value here, some hash. And now on the attacker side, yeah, now we're on the attacker side, and we basically do this replay of this guest context page with some information that we previously captured by modifying what the hypervisor does. And then if we switch back to the VM and query our attestation report again, we'll see that it has changed. So this omitted the capturing part, but this is the basic idea here. Okay, and now Jesse will walk you through the mitigations and through the second attack.
Yeah, thanks, Luca. So when we reported this vulnerability to AMD, AMD released some countermeasures. And during our experimentation, we also noticed that Intel already deployed some countermeasures before we even looked at this. And these countermeasures are basically alias checking and ECC-based metadata, which I'll go through quickly now. So the idea for the alias checking is basically that at boot time, the processor will verify the memory controller's configuration to ensure that no aliases are present in the physical memory space. And a naive way you could think about how you could do this is for every memory address, you just write some magic value and see if you can read it from some other address. So if you can read it, that means that there's a memory address, alias, sorry. Now, this is not very efficient, but if you think about this cleverly, you can actually do this in logarithmic size in terms of the module's memory size. But of course, this introduces a time of check, time of use kind of issue because this check is only performed once at boot time. And we'll actually see later how this can actually be a problem. Now, Intel actually has a second kind of defense that is storing metadata in the ECC bits of the DRAM. So they actually repurpose some of the ECC bits to store metadata, such as an owner bit that identifies secure and non-secure cache lines in memory. And for TDX, they also store a cryptographic MAC in the ECC bits. So they store a 28-bit MAC that is able to provide cryptographic integrity protection for these memory accesses. Now, I'll quickly now talk about the next kind of attack that we did. And we basically looked at this alias checking, which is only performed at boot time. Now, this effectively mitigates the BadRAM attack because this SPD is only read out once at boot time, and any subsequent changes to the SPD will only take effect on the next boot. So this one-time check will effectively mitigate this type of attack. So that got us thinking, like, is it possible to introduce these kind of memory aliases at runtime, right? So the basic idea here is that when we send our DRAM address to the physical DIMM, this will travel over the memory bus of the platform, right? So if we send out the row 1001, the DIMM will receive this. So if there is some way we can manipulate this address bus to, like, even change a single bit in the address. So if we change row 1011 to 1001, this will effectively go to a different location in the DRAM. And to understand how this is exactly possible, we have to look at the command encoding. So this is a command encoding for DDR4. So on the rows, you see the different commands that the CPU will send, such as an activate command or a read or write command. And then the columns are the physical pins that connect the CPU and the DRAM. So you have 18 address pins and then some other pins like chip select and activate. And basically the value of these pins defines the commands. And you see that most pins are, like, the value of most pins depends on the actual command that is being sent. But interestingly, 3 of these pins are only used to specify a row address bit. So for all other commands other than the activate commands, these 3 bits only have to hold some arbitrary valid value. So they can be low or high, it doesn't really matter. And so that kind of allows us to do this kind of idea that I mentioned before. So if we just add a simple switch on one of these lines, just a simple switch that can allow us to connect either this bit from the CPU or connect it to ground, we can dynamically introduce these kind of aliases. So at boot time, when this memory aliasing check is performed, we just have this switch be inactive. We just connect the CPU to the DRAM. But when we want to do the attack, we switch this line to ground. And this allows us to, again, introduce these physical memory aliases. Because now, again, we have 2 different addresses on the CPU side, where this A13 bit is 1 or 0, that map both to the same location in the DRAM, where this bit is 0. And so we implemented this on an interposer. So you can see here we have a simple analog switch connected to like a microcontroller to drive this switch that allows us to perform this attack. So we tested this on a few different server systems, and this actually works stable at any DDR4 frequency, and is also like completely deterministic and is also entirely invisible to the CPU. So the CPU cannot detect it because it's only modified after the signals leave the CPU. Now, there are some limitations because it does create unstable memory regions due to parity checking on the memory bus. But if you're interested in that, I don't have time to go now into the details, but you can talk to us later. And so this primitive, this interposer, allowed us to basically mount the SEV attack that Luca described before on patched systems, so on the latest patched systems with this alias check enabled. And it also allowed us to look at Intel's scalable SGX, because now we had a way to bypass this boot time alias check. And the interesting thing about scalable SGX is that scalable SGX actually only has a single memory encryption key for all enclaves running on the system. And the only difference is that they have an address-based tweak, so different addresses map to different ciphertext, but all different enclaves use the same memory encryption key, and that allows us to actually access arbitrary plaintext of victim enclaves. And to see how this works, let's walk through a small example. So we have a victim VM that has some secret data that is sourced to DRAM, and we then allocate some buffer to an aliasing address. Now, when we enable our interposer, we can basically redirect this read to the victim location and read out its ciphertext. Now, SGX uses address-based tweaks, so we don't actually see the plaintext yet. We just see some other ciphertext. But now the idea is we just evict the victim, allocate a second attacker enclave at this page, and just replay the data we captured into the attacker page. And because SGX uses a single encryption key for all enclaves, we actually get arbitrary plaintext access. And this allows us to kind of break any kind of enclave running on the scalable SGX DDR4 platforms. And as a small example of what you could use, what you could break with this, we looked at Intel's provisioning chain. So for attestation, Intel with scalable SGX has moved to kind of a certificate chain where you have this provisioning certification enclave that is used to sign quoting enclaves, and this allows third-party quoting enclaves. And the way this is implemented is that there's a secret hardware key embedded in the CPU that is known by Intel, and it is used to generate the provisioning certification key. And so the way we attack this is looking at how these quoting enclaves are signed. So basically what the provisioning certification enclave does is it loads this provisioning key from the hardware. It then does some seed generation and then derives the secret ECDSA key. So what we simply do is we let this PCE, which is signed by Intel and thus can access this key, we just retrieve this key and then just interrupt it before it erases its key from memory. And then we use our arbitrary plaintext access primitive to extract this key. And this allows us to extract this hardware key and sign arbitrary quoting enclaves without even having the need to have access to the system after we extracted this key. So this again completely breaks the attestation chain of scalable SGX. Now, let's talk about more principled countermeasures than the one that are currently implemented in these Intel and AMD systems. So we saw before that they currently employ alias checking and ECC-based metadata, but to completely mitigate any kind of aliasing attacks, you would have to move to more principled attacks, such as moving back to these strong memory encryption engines, such as the original SGX had, where you have both integrity and freshness again. But these seem to be abandoned by both Intel, AMD, and ARM because of the overhead and size limitations that these come with. You could also try to kind of integrate your memory into a single package, but of course for server systems this doesn't seem very likely. So to summarize, BadRAM creates physical memory aliases that can bypass these hardware-enforced access control schemes and only at a cost of like $10. This can completely compromise AMD SEV's attestation. And based on our disclosure, AMD has actually implemented countermeasure, and we also see that Intel has deployed countermeasures to prevent this. But these countermeasures come with a kind of drawbacks in that they're only performed once at boot, which allows kind of more dynamic interposer-based attacks to bypass these. And this allows us to reproduce the AMD SEV attack and completely break Intel's scalable SGX. So that was our talk. So we're happy to answer any questions. Yeah. So, no, because DDR5 actually changes the command encoding. So Patrick talked a little bit about this. So DDR5 introduces multi-cycle commands, which basically means that if you try to fault a single bit, you will also affect some other bits. And actually for server systems, it's worse because it's not a 2-cycle command, it's a 4-cycle command, and you have parity checking on this bus. So it kind of complicates this kind of attack. So the current way of just faulting a single bit is not possible on DDR5. So we did, but so this LPDDR system, so they're soldered, so like interposing will be kind of difficult, like Patrick already mentioned. And the way they communicate their size is they have some read-only registers inside the package itself. So we cannot really modify the data there and overwrite it to generate these kind of aliases.
That's basically what's already happening. Jesse shortly mentioned that there are these tweaks. So basically, we have this memory encryption key, and then for each memory address, we have a tweak value which you XOR to the plaintext before encrypting to prevent these basic ECB attacks where the same plaintext encrypted at different locations leads also the same ciphertext. Yeah, so that would not really help there.
Could you comment on how whether this is scalable for solder DIMMs?
Yeah, so you mean about the first BadRAM type of attack, or
Sorry?
you mean about the BadRAM or the interposer style attack?
Either.
So I quickly, like I already mentioned this briefly before, so these to do the BadRAM attack, you would have to change this metadata, but this is stored in read-only registers inside the LPDDR package, so we cannot modify those. And interposing is kind of difficult because they're soldered, so there are interposers you can install between them. They're mostly used for memory testing, but it would get kind of messy and tricky, I think.
Okay, let's thank the speakers.